Hi, this is James, and in this video I will present some notes on Gaussian, Radau, and Lobatto quadrature, as well as the theorem of Bernstein. I will cover the role of orthogonal polynomials, the Golub-Welsch algorithm, the error, and the interleaving property. The level of mathematical sophistication is intended to be roughly calculus 2. A quadrature formula approximates a definite integral as a sum over the n nodes, xk, where n is the order of the formula, of the functional values at the nodes, times some weights wk. In Gaussian-type quadrature, it is possible to introduce a weight function, omega of x, which is non-negative, doesn't incorporate Dirac delta functions, and for which this integral converges for any polynomial p of x. The weight function could decay fast enough that either of the limits of integration could be infinite. It may also be possible to factor an integrand into a weight function times an analytic function and develop a Gaussian quadrature formula with the non-analytic weight function, getting a more accurate approximation for the effect of the analytic function. The degree of a algebraic exactness, or simply the degree of a quadrature formula, is the highest degree of the formula, highest degree of polynomial for which the formula is always exact. If the degree n is greater than or equal to the order little n minus 1, the formula is interpolatory. Let pi n of x be the monic polynomial of degree n with the n nodes as its roots. Then the interpolatory quadrature formula applied to the integral is exact, and the integral is 0 at all of its nodes except for xk, where its value can be determined by L'Hopital's rule, yielding the simple formula for the weights wk. If we insert that formula into the Gaussian quadrature formula and reverse the order of summation and integration, we get the same result as would be obtained by substituting the unique polynomial of degree at most n minus 1 that goes through the points xk, f of xk in the original integrand. The degree of a quadrature formula can't be twice its order, because if we define pi star of x as shown, then the quadrature formula for this integral produces 0, but that's incorrect because the integral is inherently positive. If n equals 2n minus 1, the quadrature formula is said to be Gaussian. We will provide an example to show how the nodes and weights could be worked out in the general case. This might be the preferred method if tasked to do this in a test, because it doesn't require remembering any formulas. Be warned, however, that this method is not numerically suitable for large n. Here, our limits are from minus 1 to 1, and the weight function will be the triangular pulse function shown in figure 1. There's figure 1. We can work out the integrals here for j equals 0 to 5, and so obtain 6 equations for the 3 nodes and the 3 weights wk. 6 nonlinear equations and 6 unknowns can be quite daunting, but in the Gaussian quadrature case, there's a straightforward procedure. First, we rewrite the equations in matrix form here, then write out the augmented matrix for the system and perform Gaussian elimination. For Vandermonde matrix, the trick is to eliminate from the bottom up. Subtract x1 times row 5 from row 6 to produce a 0 here. Boop. Then work our way up the first column to produce 4 more zeros. Boop, 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 boop. The same procedure with x2 instead of x1 to create 4 more zeros in the second column. Boop, 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 boop. And then make 3 zeros in the third column. Boop, boop, boop. The fourth row now says that 0w1 plus 0w2 plus 0w3 equals 0 equals this stuff. And so we can see that the last 3 rows, this one, and this one, are now 3 linear equations in the 3 unknowns S1, S2, and S3, rewritten like this. We can solve these and then use the fact, so here is solving them, and then use the fact that the monic polynomial of zeros at x1, x2, and x3 has coefficients that are plus or minus s1, s2, and s3. To get this equation, we can solve for x1, x2, and x3. So there's our x1, x2, and x3, and we're going to write those in increasing order. Now we can back substitute these results into the first 3 rows. To get from this, we would get W3, and now we can get from this W2 and this W1. So now that we know W3, W2, W1, we have found the 3-point Gaussian quadrature formula. Boom. We will see immediately that Gaussian quadrature formulas imply orthogonal polynomials, so we explain their definition and properties. Given any f, a polynomial of degree at most n-1, this integral must vanish if the quadrature formula is Gaussian, because every term of that sum would be 0. 2 functions are orthogonal if to each other if the integral of their product times the weight function omega of x is 0. Equation 6 says that pi n of x is orthogonal to all polynomials of lesser degree. Such a polynomial is called an orthogonal polynomial. Starting with pi naught of x equals 1, we can use this formula inductively to establish the existence of a pi n of x for each n greater than 0. That's how this formula would work. And that's called the Graham-Schmidt process. Given another monic orthogonal polynomial of degree n, rho n of x, we know that pi n star minus rho n star is of a degree at most n minus 1 because both those polynomials were monic. And so it's orthogonal to both pi n of x and rho n of x. So that means that this integral here, which is the integral of an absolute square times a non-negative weight function, is 0. So it must be that pi n of x minus rho n of x is 0. The next integral here, boom, is 0 by orthogonality. If we multiply numerator and denominator by x minus xk and separate real and imaginary parts, this integral is positive, so that means that the imaginary part of the root xk is 0. And the rest of this integrand, here's the rest of it, is non-negative, so x minus the real part of xk must change sign in the interval of integration, so the real part of xk must lie in the open interval from a to b. If xk were a simple root, were not a simple root, then this integral would be 0 by orthogonality, but we can regroup it like this, which is positive, and so that means that xk being non-simple leads to a contradiction. Thus, given a, b, and omega of x, satisfying the three properties we have established, the existence and uniqueness of the orthogonal polynomial pi n of x, whose roots are all real and simple and lie inside the interval of integration. Okay, if f of x is a polynomial of degree at most 2n minus 1, we can divide it by pi n of x to get a quotient polynomial, qn minus 1 of x, and a remainder polynomial, rn minus 1 of x, both of degree at most n minus 1. And now we try to perform our integral, and we find that this quotient part vanishes by orthogonality, and in equation 2, we showed that there is a unique set of weights w sub k that makes the quadrature formula exact given that given that our formula is interpolatory. Okay, then we can restore qn minus 1 of x pi n of xk because it's 0, and so establish that the quadrature formula with nodes at the zeros of the orthogonal polynomial pi n of x is exact for any polynomial of degree at most n minus 1, 2n minus 1. Equation 2 implies evaluating a separate integral for each weight, or for each node actually, but we can evaluate this integral on the left by applying the Gaussian quadrature formula and Lobatto's rule, and on the right, because this much is orthogonal to pi n minus 1 of x, so that reduces to this, and only one integral here suffices for all the weights. There are techniques for finding the nodes and weights of a Gaussian quadrature formula if their orthogonal polynomials satisfy a Sturm-Liouville differential equation, which I intend to cover in subsequent videos. But there is an algorithm which may be applied in the general case, the Golub-Welsch algorithm. we can expand x pi n of x as a linear combination of orthogonal polynomials of degree 0 through n plus 1, as done here. Choose any m less than n minus 1 and multiply both sides of the equation by omega of x pi m of x and integrate on. So on the left, we get 0 by orthogonality, and on the right, the procedure picks out the term with the coefficient of pi n of x by Fourier's trick. This shows that am is 0 for m less than n minus 1, so only the top three terms survive in our expansion up here. Since pi n of x is monic, it follows that an plus 1 is 0, so we have arrived at this. Well, if n equals 0, we get this with only two terms. We could multiply both sides of this equation by pi naught of x and times omega of x and get an expression for beta naught after we integrate. If we knew these two integrals, this one and this one, we could similarly, okay, so now if we knew these two integrals, we could similarly determine beta n, okay, from this equation. For n greater than or equal to 2, we can substitute for pi n of x in this integral here to get this, and apply orthogonality to get to here, and then substitute for x pi n of x, get us to here, and apply orthogonality again to get this. Taking into account that there is no gamma naught, or pi sub minus 1 of x, we still get this expression for n equals 1. This completes the recursion. Knowing pi n of x, we can determine beta n by this, and gamma n, we can determine beta n by this, and gamma n by this, and so find pi n plus 1 of x by this. Also, it relates the normalizations of all the pi n of x. Now, if we define Pn of x to be orthogonal polynomials with common normalization and positive leading coefficients. In terms of these polynomials, we can write our recurrence relations as this, and this for n equals 0. If Pn of x equals 0, if Pn of xk is 0, then the initial equation reads this, and for 2 less than or equal to I less than or equal to n minus 1, the equations read this. Well, for I equals n, because Pn of xk equals 0, we get this. We have written out these equations as the row of a matrix equation with vector pk defined here. Thus, we have restated the problem as an eigenvector problem. There. Careful inspection of our equations that give us the entries of A tell us that it is a symmetric tridiagonal matrix. And there are lots of programs available to solve this kind of problem. Given a solution, xk is a node of the Gaussian formula, and to get the weights, we start with this integral, and apply the quadrature formula, getting to here. Then we pick out this much, the sum on I with this and this, and that's just the scalar polynomial of the vector pk with the vector pj. Since eigenvectors belonging to different eigenvalues of a real symmetric matrix are orthogonal to each other, as shown here, it simplifies to this and then this. On the other hand, we could have evaluated the integrals directly, relying on the fact that pi of x is orthogonal to p naught of x is 1, and for I greater than 0, the pi of x is orthogonal to p naught of x for I greater than 0, and then simplify to this. There is a well-known formula for the error in Gaussian quadrature formulas, but its proof is a little tricky because of the possibility that the interval of integration is not necessarily bounded, nor are the derivatives of f of x. First, we assume that the integral we're trying to approximate converges. Then we can find a unique polynomial, hn1 of x, whose functional values and first derivatives agree with f of x at all n nodes of the Gaussian quadrature formula. Let S be the set of nodes xk of the Gaussian quadrature formula. We will assume that f2n of x is continuous on the open interval from a to b. Choose any v in the open interval from a to b, but not in the set S. We can construct a polynomial of degree 2n that agrees with f of x and f prime of x at the nodes xk, and also agrees with only f of v. The difference between f of x and this polynomial is e of x. Since e of x is 0 for x in the set S union the set consisting only of v, that's n plus 1 zeros. And so by Rolle's theorem, e prime of x has n zeros in the open interval from a to b. Forget about S union v. Also, e prime of x is 0 by inspection for x in S, so that's n more zeros. So e prime of x is 0 n times in the open interval from a to b. Applying Rolle's theorem 2n minus 1 more times, we get to here. This produces the error here for v in AB, forget about S. Solve for f2n of xi of v, we can see it's continuous for v and ab, forget about s, and it reaches a limit as v approaches xk, an element of s. So we can define f2n of xk, of xi of xk by this limit, making it continuous for all v in the open interval from a to b. Then this integral converges because it's the difference between two convergent integrals, and that defines in. We can also define jn and omega n. And omega n is continuous because, remember, omega of t didn't contain any Dirac delta functions. And it's increasing because the integrand is non-negative. Well, non-decreasing, actually. Whether the interval of integration is bounded or not, so that's like 4 cases I outlined here. There is a suitable A1 such that this holds by the definition of a limit. Similarly, there is a suitable B1 such that this holds. Then, by the intermediate value theorem, we can find an A3 and a B3 such that the integral Jn can be divided into 3 equal chunks, all equal to 1/3 Jn. Now we have 4 cases according as the 2nth derivative of f is bounded above or below or not. And here we have, keep in mind that Rn is In over Jn. The difficult case is where it is bounded. Like if we look in case 1, we see that if it's not bounded, we can find an f2n of d that's bigger than Rn and f2n of c that's less than Rn, and apply the intermediate value theorem to find an f2n of xi that is actually equal to Rn. So now here, if we assume it's bounded above but not below, and here's our least upper bound, in this case, we can go back to 35 and focus on this okay. We can show from 35 that this middle integral here has got to be 1/3 mjn. And it's over a closed interval, so we can apply the extreme value theorem to establish that f2n of eta equals m for some eta in the open interval from a to b. Working through all the other cases, we arrive at this equation 39, where we see that the error in the Gaussian formula is some constant times the 2nth derivative of f of xi for xi in the open interval from a to b. That's saying that the Gaussian quadrature formula is definite. Gaussian quadrature formulas that have all positive weights, WK, Gaussian quadrature formulas have all positive weights, WK, as shown here. Well, we'll show it pretty soon. And being extreme in some sense, they also put constraints on other formulas with all positive weights. So here's the simple proof that Gaussian formulas have all positive weights. Suppose we had an alternative quadrature formula with degree at least as high as the Gaussian quadrature formula, at least one node not equal to any of the Gaussian nodes, and all positive weights. This integral here shows that Zm is greater than Xn, because if that weren't true, there would be no positive terms in the sum, and we know there's one non-zero term in the sum, so there must be both positive and negative terms. And then this integral shows that Z1 is less than X1, similarly, or all the terms, or there would be no negative terms in the sum. And this guy shows that there is a zk between each pair of nodes, xj and xj plus 1, of the Gaussian formula. So that's the interleaving property, and it implies, first off, that between each pair of zeros of pi n of x, there's a zero of pi n minus 1 of x, well, if n is bigger than 1. So the sequence of polynomials, orthogonal polynomials in decreasing degree order, is a Sturm sequence. A Cronrod extension of a Gaussian quadrature formula uses the Gaussian nodes, has all positive weights, and at least the degree of the Gaussian formula. The interleaving property dictates that it must have at least 2n plus 1 nodes. Okay. Now, in this equation, all terms are non-negative, and pi n of x over x minus xn squared is increasing for x bigger than xn, and you know that Zm is bigger than xn, so pi n of x, this guy, has got to be bigger than pi n of xn squared. So that means that Qm, the last weight of the alternative formula, must be less than Wn, the last weight of the Gaussian formula. Now we get up to here, a Chebyshev-type formula, which has the interval from -1 to 1, omega of x is 1, and it has all the same weights, 2 over m. Then this common weight 2 over n has to be less than W sub n for the n-point Gauss-Legendre formula. Okay, now we do have a nice approximation for Wn in terms of Bessel functions, so we end up with this nice little inequality for the order of yes, for the order of the formula given the degree of the formula. So now in figure 2, I am plotting the maximum degree, big N, versus the order of a Chebyshev-type formula, little m, and also the Bernstein bound that we showed up there. And we can see it stays pretty close to the Bernstein bound. Now, I can't guarantee the accuracy of these points given what we know about boomers and their cantankerous Fortran programs. What we know about Gaussian quadrature formulas may be applied to Radau quadrature formulas. Now, we could choose an n plus first point that's fixed at the left end point with still n floating nodes. Now, the degree of such a formula has to be less than 2n plus 1 because here I've got this polynomial of degree 2n plus 1, and when I do the integral, well, that integral is non-negative, so the integral is positive, but the quadrature formula that we would get if it had order 2n plus 1, if it had degree 2n plus 1, would have to be 0. Now, if n is 2n, the quadrature formula is a Radau formula. Now, if the left endpoint is used as up here, it's called left Radau, whereas if the right endpoint were used, it would be right Radau. A right Radau can be shown to be equivalent to some left Radau formula. So for the remainder of this section, we will only consider left Radau formulas. We have this constraint for f of x, any polynomial of degree at most n minus 1. So that means that pi n of x is an orthogonal polynomial over the interval from a to b with weight function omega of x, x minus a. We know that pi n of x exists, it's unique, and all of its zeros are real and simple and lie within the open interval from a to b. From our analysis of Gaussian quadrature. Then, having found pi n of x, we prove that the interpolatory quadrature formula with nodes at x naught equals a and the zeros of pi n of x is exact for f of x, any polynomial of degree at most 2n. So we're going to try to evaluate this polynomial by our quadrature formula, and we're going to divide f of x by x minus a pi n of x to get quotient and remainder polynomials. And then the quotient integral part is 0 by orthogonality, and we can integrate the remainder part exactly because the formula is by assumption interpolatory. Then we can go back and put in the quotient part of xk, because it's 0 at each xk, and that reconstitutes f of x, proving that our formula is in fact exact for any polynomial of degree at most 2n. We have a nice formula for the interior weights. We start with this integral and evaluate it on the left via the Radau formula and Lobatto's rule, and on the right, because this is orthogonal to pi n minus 1 of x. So again, we can get all the interior weights with just one integral. The weight W naught is a bit more awkward. We could construct the monic polynomial sigma n of x, which is orthogonal over AB with weight function only omega of x, and write pi n of x in terms of it. And then compute this expression, expressing W naught in terms of the normalization. But this isn't very satisfactory. There is a simple solution in terms of only pi n of x for the classical polynomials, which we hope to cover in the future. We can use the Golub-Welsch procedure to find the nodes and weights of a Radau formula. We set up the procedure with the Gauss weights, just the Radau weights times x minus a, the Radau weight function. The Gauss weight function is the Radau weight function times x minus a. We set up the procedure, okay, and then we do the Golub-Welsch procedure. So that gives us the internal nodes. Comparing this formula with the Gaussian formula for the weights, we get then the Radau weights from the ones we got from Golub-Welsch. Then we just have one more integral, this one, to find W naught. I wrote out the whole proof of the error in Radau quadrature in the PDF, but I'm going to skip it in the video. You may pause and screen capture it if interested. So here's one page, here's another page, there's another page. Okay, and there we're at the end. So the result is the same. That's to say that Radau quadrature is definite. Now, it's easy to show that the weights of Radau quadrature formula are all positive. Here's the proof for W naught, and here's the proof for the other weights. If an alternative quadrature formula has degree at least as high as that of the Radau formula, and at least one node not equal to any of the Radau nodes, and all positive weights, so here's our alternative quadrature formula, we must have from here either Z1 is less than A or Zm is bigger than Xn, or there wouldn't be any positive terms. There must also be a node between A and X1 because of this little equation, and between any pair of interior nodes. The interleaving property of Radau quadrature requires the alternative quadrature formula to have a node between each pair of nodes of the Radau formula, interior or boundary, and one node either before x naught equals a or after xn. As an example, I'm just going to write out the Radau quadrature formula for this. And it has an extra, so now this formula here has an extra node after xn, and this one has its extra node before x naught. And all of these formulas have algebraic accuracy n equals 2, and all have positive weights. The interleaving property leads to the conclusion that the sequence of orthogonal polynomials in decreasing order is a Sturm sequence, and also that any Cronrod extension has at least 2n plus 2 nodes. Now we consider formulas that use both endpoints as nodes. The degree of such a formula, so here's our formula. It's using, there's the left endpoint is x naught, and the right endpoint is xn plus 1, so there's n plus 2 nodes. The degree of such a formula must be less than 2n plus 2, because the quadrature formula says that this integral is 0, whereas it's necessarily positive. If the degree is 2n plus 1, the quadrature formula is a Lobatto formula. If if f of x is a polynomial degree at most n minus 1, then this integral, just applying the Lobatto formula, is 0. So that means that pi n of x is an orthogonal polynomial over the open interval from a to b with weight function omega of x, x minus a, b minus x. We know there is a unique monic polynomial, pi n of x, a unique monic orthogonal polynomial, pi n of x, and zeros are real, simple, and lie within the open interval from a to b. We can show that the interpolatory quadrature formula with nodes at x naught equals a and xn plus 1 is b, and the zeros of pi n of x is exact for f of x, any polynomial of degree at most 2n plus 1. So I'm going to divide f of x by x minus a, b minus x pi n of x to get a quotient and a remainder polynomial. And now here I'm trying to evaluate my integral. Now the quotient part of the integral is 0 by orthogonality, and the remainder integral is exact because the formula is interpolatory. Then we can reconstitute the quotient term, because it's 0, in the sum, reconstituting f of x, and that proves that our Lobatto formula actually does work. We can find the weights of the interior nodes starting from this integral. We apply the Lobatto formula on the right, and on the left, because this much is orthogonal to pi n minus 1 of x, that middle integral just becomes this. Now, had we started with sigma n of x orthogonal over the open interval from a to b with weight function b minus x omega of x, we could get this, defining pi n of x, and then we could find w naught by a normalization integral. However, this is unsatisfactory if only because we would have to do this all over for wn plus 1. There's a simple solution using only pi n of x for the Jacobi polynomials. We could use the Golub-Welsch procedure to find the nodes and weights of a Lobatto formula. Start with this and weight function, and apply the Golub-Welsch procedure to find nodes and weights for the Gaussian formula. The Gaussian nodes now are the interior nodes of the Lobatto formula, and in comparing equations 78 for the Lobatto formula and 10 for the Gaussian formula, we see that the Lobatto weights will be this. That's the interior weights. It takes one more integral to find W naught and another integral to find Wn plus 1. The error of a Lobatto formula can be determined analogously to that of the Gaussian formula, so we skip it in the video. The interested viewer can pause and print screen for details. Okay, pause there. The result is, of course, that Lobatto formulas are also definite. Now it's easy to show that the weights of the Lobatto formula are all positive. So here's W naught, here's the proof for Wn plus 1, and here's the proof for the interior weights. Given an alternative quadrature formula of degree at least as big as the Lobatto quadrature formula, at least one node not equal to any of the Lobatto nodes, and all positive weights, we can only have a negative term here if some zk is less than a, or some zk is between xn and b. So this leads to many possibilities, and for simplicity, we're only going to consider the case where each zk is in the closed interval from a to b, and from this integral, it forces a zk to lie between xn and b. And given this constraint, we can do this to find that there must be a zk that lies between a and x1, and between any two interior nodes, we also have to have a node of the alternative quadrature formula. So that means there's a node of the alternative quadrature formula between each pair of nodes, internal or boundary, of the Lobatto quadrature formula, or some node that's outside of the closed interval from a to b, which case we're not interested in. This interleaving property implies that the sequence of orthogonal polynomials in decreasing order of degree is a Sturm sequence, also a Cronrod extension that reuses all the Lobatto nodes and has all the nodes within the closed interval of integration and all weights positive and degree at least as big as the Lobatto formula, and one node not equal to any of the Lobatto nodes must have at least 2n plus 3 nodes. A Newton-Cotes formula is an interpolatory quadrature formula with equally spaced nodes, including at the limit of integration with omega of x equals 1. Okay. If such a quadrature formula has degree big N greater than or equal to 2 little n plus 1 and all positive weights, then it follows that Zm plus 1, m minus 1, must equal to 1 minus 2 over m minus 1 has to be bigger than xn by the interleaving theorem, where xn is the largest interior node of the n plus 2 point Lobatto quadrature formula over the interval, closed interval from -1 to 1, with omega of x equals 1. An approximation for xn from the Lobatto formula produces the it produces the Bernstein bound. This led to the proof of the theorem that a Newton-Cotes formula must have a negative weight for m equals 9 and for m greater than or equal to 11. Now in figure 3 here, we're going to plot the exact maximum degree and for a quadrature formula with weight function omega of x equals 1 and n equally spaced nodes, including limits of integration. As in figure 2, we can see that the actual bound on n is pretty close to the Bernstein bound, at least for small m. I would like to produce videos on figures 2 and 3 in the future, but for now I must thank you for your kind attention to my video, and until next time, try to think quantitatively and creatively.